For today's MEB class, I have a couple of problems that will illustrate how to use the ideal gas law in the course of solving them. The first one says a tank of nitrogen, N2, has a volume of 100 cubic feet and an initial temperature of 80 Fahrenheit. If 1 pound mass of N2 is removed and the pressure drops to 100 psi, gauge, while temperature drops to 60 Fahrenheit, calculate the initial reading on the temperature gauge. I have a lot going on here in this problem that doesn't look like it initially. So as I always do, I'm going to start with drawing myself a picture. And once again, you are encouraged to pause the video here and try to solve this on your own before I do it. I think you learn a lot more when you try your hardest to solve a problem before you just watch me do it. I'm going to draw two pictures. One of them is going to be the initial state of the gas, and the other is going to be the final state of the gas. So nitrogen tanks are not boxes in real life, but it helps to visualize them that way. And I'm going to assume, however poor of an assumption that this is, 100 psi gauge. That's a pretty large pressure. That is at least 4 or 5 atmospheres, right? So it's unlikely that the gas is going to behave ideally at this high of pressure. But I'm going to assume that it is ideal for the purposes of solving this problem. Just know that when you get into your thermo class or your phase class, you will likely not be able to make this assumption. So I've got PV, NR, and T, and PV, NR, and T. And I'm going to write what I know from the problem statement. The tank of nitrogen has a volume of 100 cubic feet. I'm going to label that. This is my initial state. And it's a reasonable assumption to make that a nitrogen tank is going to be rigid. In other words, the volume of the tank is not going to change no matter what. If it's made out of steel. Now, if it's flexible or made out of some material that can move or the boundaries can move, yes, the volume can change. Or if you have a stand-up paddle board, say, where the volume inside can change, that would be possible. But for most canisters of gas, volume is going to be rigid. The initial temperature is 80 Fahrenheit. The final temperature is 60 Fahrenheit. I don't know how many moles of N2 I have, so I'm going to label this as N1 and label this as N2. But I do know that 1 pound mass of N2 is removed. So I'm going to label that. 1 pound is removed. And I'll make sure to label that N1 is going to be in pound moles, LB moles. All right, and I know that it's nitrogen, so I can convert what those moles are. The pressure is, what is it originally? Pressure drops to 100 psi gauge. So pressure is 100 psi G. And my goal is to calculate the initial reading on the pressure gauge. So what is P1? So if I look at what I have in this problem, I can calculate what the gas constant is, or I can look up what the value of the gas constant is. So it's not that big a deal that I don't have it yet. But I have one unknown in my final reading, right? The only thing I don't know is N2. And if I know that N2 is with 1 pound removed from the situation in N1, if I can solve for N2, I can then solve for N1, and I can then therefore solve for P1. So that's going to be the overall sketching out of the solution procedure. Now, before I begin, remember, anytime I do an ideal gas law, so for the final situation, I can say that PV is equal to nRT. And since I'm trying to solve for N2, I could say that N2 is P2V2 over RT2. And I have all these numbers, but I'm not just going to simply plug in everything I've written so far. Remember that anytime I'm doing an ideal gas law calculation, I must have absolute pressure. So I'm going to cross out this 100 psi G and instead write the absolute pressure, 114.7 psi A. So that is the gauge pressure plus the atmospheric pressure is going to give me absolute pressure. Volume is fine how it is, so I don't have any absolute volume considerations or anything like that. But temperature, I have to change. I cannot do temperature in the Fahrenheit scale. I must instead do it in the Rankine cycle. Not Rankine cycle. Rankine cycle is something else that you learn in thermodynamics. Rankine scale is what I had meant to say. And the conversion is plus 459.67. So 60 Fahrenheit is equivalent to 519.67 degrees Rankine. Remember that Rankine is the analog to Kelvin, but for the Fahrenheit scale. So this is degrees Rankine is a temperature in absolute scale based on Fahrenheit. The last thing I need is to look up the value of my gas constant. So in any table of the gas constants, this one's also a fairly common one that you should be able to find. It's 10.73 in cubic feet PSI per pound mole degree Rankine. So this is the same thing, 8.314, but this is just in the English unit system. So now I have an equation, so I can plug in 114.7 PSIA times 100 cubic feet over 10.73 cubic feet PSI per pound mole degree Rankine times 519.67 degrees Rankine. My units are going to cancel out in order to get me pound moles at the end. So I just crunch this number, and my moles, if I solve for N2, it's going to be 2.06 pound moles. Okay, so my final situation is now resolved. Now I'm going to use the information that I have. So this N2 is with 1 pound mass being removed. That is what LBM stands for. Therefore, N1 is going to be 2.06 pound moles plus 1 pound mass of N2. And as I said in the very first week of the class, this is not a dimensionally consistent equation. I cannot add pound moles to pound mass. So if I want to figure out what the pound moles are, I have to convert this mass of nitrogen to pounds. Sorry, convert this mass to moles of nitrogen. So I'm going to multiply by the molar mass, divide by molar mass more appropriately. So there's 28 pounds per 1 pound mole. Had some questions about this last week. Remember that pound mole, kilogram mole, those are all different ways of defining the mole, but the number, the 28 stays the same. So it's 28 pounds per pound mole, 28 grams per gram mole. Okay, but doing this calculation now, if I convert and just add these two then, 1 divided by 28 is not really that much at all. So I get that N1 is equal to 2.09 pound moles. So R again is 10.73, N1 is 2.09. And now I have another PV equals nRT equation that I can solve. This time I want to solve for P1. And this P1 is going to be in absolute pressure. So P1 is equal to N1 RT1 over V1. N1 was 2.09. R is 10.73. Getting sloppy and omitting the units, but I know that the units are going to cancel out. Oh, 80 Fahrenheit, I need to convert that. That is going to be 539.67 Rankine. So again, just adding 459.67, all divided by 100 cubic feet. This calculation works out to 121 PSIA. And because the problem specifically asks, what is the initial reading on this should say pressure gauge, by the way. I just noticed that. Or it wouldn't make any sense. They told you what the initial reading on the temperature gauge was. We want to find the initial reading on the pressure gauge. That is going to be gauge pressure. So initial reading on pressure gauge, not temperature gauge, is 121. This is 0.02, by the way, if I wanted to carry out one more significant figure. Minus 14.7 is 106.3 PSIG. Now, before I finish this video, I just want to note that there's a more elegant way that you could solve this equation that does not require you to know what the gas constant is. So instead of doing it how I did it, I could have said P1 V1 over P2 V2 is equal to N1 R T1 over N2 R T2. Then also as a note, typically when you write PV equals nRT, the n is lowercase, but in this class, I've been writing n as uppercase. That's the same thing. Don't get confused by that notation change. If I write a ratio of these ideal gas laws, the gas constant is going to cancel out. So if I wanted to calculate what the initial P was, I could simply rearrange this equation and say that P1 is equal to N1 T1 over N2 T2. And that's also another reason why I want to do this is because V1s are going to cancel out because they're the same for this particular problem. So I don't even have to worry about it as much, is equal to P2. I still would have to figure out what N1 and N2 would be though. Right, so I would still have to write, if I wanted to do this, I'd still have to figure out what N2 was. Yeah, so actually you still would need to know what the gas constant is in order to find N2 in order to then find N1. But I show you this just because whenever you're comparing two ideal gas laws, it sometimes is instructive to write them as a ratio such that all common terms cancel out, and then the calculation might get a little bit easier. So that'll be it for this video. I've got one more practice problem coming up.